Dynamic programming is one of the most important algorithmic techniques you'll encounter in technical interviews. It's a powerful method for solving optimization problems by breaking them into smaller, manageable subproblems. The key concepts we'll master today are memoization, which uses a top-down approach with caching, tabulation, which builds solutions bottom-up iteratively, and various optimization techniques that will help you tackle classic interview problems efficiently. Dynamic programming is built on two fundamental principles. First is overlapping subproblems, which means the same subproblems occur multiple times during recursive computation. For example, when calculating Fibonacci numbers, f of n-1 and f of n-2 are computed repeatedly. Second is optimal substructure, where an optimal solution contains optimal solutions to its subproblems. Think of finding the shortest path between 2 points. The optimal path will contain optimal subpaths between intermediate points. Memoization is the top-down approach to dynamic programming. The core idea is to cache and reuse computed results to avoid redundant calculations. When we store results in memory, we transform an exponential time algorithm into a linear one. In our Fibonacci example, we use a memo dictionary to store previously calculated values. Before computing any Fibonacci number, we first check if it exists in our memo. This simple optimization reduces time complexity from O of 2 to the power n to O of n, while using O of n space. Tabulation takes a bottom-up approach to dynamic programming. Instead of using recursion, we build and fill a table iteratively, solving the smallest subproblems first and building up to larger ones. In the Fibonacci tabulation approach, we create an array and initialize the first two values. Then we iterate from index 2 to n, filling each position by adding the two previous values. This method also achieves O of n time complexity and O of n space complexity, but avoids the recursion overhead entirely. Let's compare these two approaches. Memoization uses a top-down recursive approach, solving larger problems first and breaking them down. It requires extra recursion stack space, but has the advantage of only computing subproblems that are actually needed. Tabulation, on the other hand, uses a bottom-up iterative approach, solving smaller problems first. It has no recursion overhead and typically uses less space, but may compute subproblems that aren't necessary for the final answer. Dynamic programming shines in two main categories of problems. Optimization problems include the 0-1 knapsack problem, where we maximize value within weight constraints, coin change problems for finding minimum coins needed, edit distance for string transformations, maximum subarray sum, and house robber scenarios. Sequence problems focus on finding patterns in data, such as longest common subsequence between strings, longest increasing subsequence in arrays, palindromic subsequences, word break problems, and unique path counting in grids. The 0-1 knapsack problem is a classic optimization challenge. Given items with specific weights and values, we need to maximize the total value while staying within a weight constraint. Each item can only be taken once, hence the name 0-1. The dynamic programming solution uses a two-dimensional table where dp of I, W represents the maximum value achievable using the first I items with weight limit W for each item. We decide whether to include it or not by comparing the value of taking it versus leaving it. The time complexity is O of n times W, where n is the number of items and W is the weight capacity. Longest common subsequence, or LCS, is a fundamental string matching problem. Given two strings, we find the longest subsequence that appears in both strings in the same relative order, but not necessarily consecutively. For example, with strings ABCDGH and AEDFHR, the LCS is a DH with length 3. The DP solution creates a table where dp of I, J represents the LCS length for the first I characters of string X and first J characters of string Y if characters match. We add 1 to the diagonal value. Otherwise, we take the maximum of the left and top values. The longest increasing subsequence problem asks us to find the longest subsequence in an array where elements are in strictly increasing order. For the array 10, 9, 2, 5, 3, 7, 1, 0, 1, 18, the LIS is 2, 3, 7, 18 with length 4. The basic DP approach uses a one-dimensional array where DP of I represents the length of the LIS ending at index I. We initialize each position to 1. Then for each element, we look at all previous elements. If a previous element is smaller, we update the current position to be the maximum of its current value, or the previous LIS length plus 1. Matrix chain multiplication focuses on finding the optimal way to parenthesize a sequence of matrix multiplications to minimize the total number of scalar multiplications. When multiplying matrices A1, A2, A3 with dimensions 5 by 4, 4 by 6, 6 by 2, we can parenthesize as either A1 times A2, then times A3, or A1 times the result of A2 times A3. Different parenthesizations lead to different computational costs. The DP solution uses interval dynamic programming, considering all possible split points for each subchain and choosing the one that minimizes the total multiplication cost. Once you understand basic DP, several optimization techniques can dramatically improve performance. Space optimization techniques include using one-dimensional arrays instead of two-dimensional ones, implementing rolling array techniques to reuse space, and tracking only necessary variables. Time optimization methods include using binary search for problems like longest increasing subsequence to reduce complexity from O of n squared to O of n log n, matrix exponentiation for problems with linear recurrence relations, state compression for reducing memory usage, and convex hull optimization for specific types of DP transitions. To master dynamic programming in interviews, follow these strategies. For problem solving, always start by identifying optimal substructure and overlapping subproblems. Choose between memoization and tabulation based on the problem constraints. Begin with a brute force recursive approach, then optimize step by step. For interview strategy, practice classic DP problems until they become second nature. Always explain your thought process clearly to the interviewer. Write clean, readable code with meaningful variable names. Analyze both time and space complexity of your solution. Finally, test your code with edge cases like empty inputs, single elements, and boundary conditions. Remember, practice makes perfect, so keep coding and building your DP intuition.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.